Hello, my name is Pierre Martre. I'm giving this presentation today on model-aided phenotyping with my two co-authors, Chiang Liu and Fred Barry. One of the main challenges for plant phenomics is to transform big data into knowledge. This requires articulated workflows that integrates different types of models with increasing interpretation complexity and prior knowledge of physiological processes. Facilitate the development of workflows for phenomics, we created the digital plant phenotyping platform, D3P. This platform that I will present today integrates functional structure on plant model uh, implemented in the OpenArea platform and that simulate the growth of 3D virtual canopies. These canopies can be analyzed using simulators of RGB, multispectral, or LIDAR sensors that produce images and point clouds of canopies that can be analyzed using different types of model to estimate canopy traits. Thousands of virtual canopies can be produced by perturbating the inputs of the 3D models. Here we created over 2,000 width canopies by perturbating 5 influential parameters identified from a sensitivity analysis of a model and trained a neural network to estimate these parameters. I'm here presenting result of the estimation of 3 parameters estimated during the early growth phase of the crop between crop emergence and beginning of stem extension. So we estimated the rate of leaf emergence, the fulcrum, the length of leaf one, and the rate of leaf length increase. These 3 parameters were estimated with a relative error of less than 10% for the first 2 parameters, even when a random error of 10% was introduced in the pseudo observations. And the third parameter, the rate of leaf length increase, was estimated with an error of 20 to 30%. But the green area index was estimated with an error of less than 10%. So the information on these 3 early stage parameters was used as a prior information to train a second neural network to estimate parameter determining the growth of the canopy during the stem extension period. And we were then able to estimate during that period the green area index of the canopy with a good accuracy of less than 10%, and we're also able to estimate the number of tillers at the end of the leaf production phase with an error of about 15%. The D3P platforms can also be used to optimize measurements configurations. It's not possible to evaluate in the field all possible sensor configuration or measurements return time. Therefore, we developed a simulation protocol to evaluate a large number of combinations of sensor configuration and measurement return time, and we found that the base compromise between the accuracy of trait estimation and the cost associated to the multiplication of measurements and devices is when measurements are made at 0 and 60% from the vertical and repeated every 100-degree days. A key parameter to estimate the fraction of intercepted light by canopy is the inclination distribution of green elements of canopy. But very little information is available in the literature on this parameter. So we extracted from the field rows of undisturbed canopies that we digitalized to calculate the distribution of green elements of canopy at different growth stages for cultivars with contrasted leaf stature. And we found that the leaf angle distribution of these different canopies can be accurately represented with an ellipsoidal model. A key parameter of this model is the leaf angle distributions, which can be estimated from D3P using imagery at 0 and 45 degrees. And so with this estimation of the average leaf angle that we can use as inputs of turbine medium model with ellipsoidal leaf angle distribution to estimate the fraction of intercepted PAR with a good accuracy, both of a direct PAR in different directions, different angles, and also for diffuse PAR. So we train a neural network to estimate the fraction of intercepted PAR, the green area index, and a key parameter of canopy structure, the average leaf angle distribution. And we evaluated the capacity of this, the ability of this trained neural network to estimate canopy structure and light interception of with canopies in the field. So we phenotyped a large number of canopies using a phenomobile equipped with 2 cameras placed at 0 and 45 degrees from the vertical, and so use this neural network to estimate these 3 parameters. So I'm here presenting results for one as an example of one durum wheat varieties grown over 3 consecutive years in south of France under irrigated and non-irrigated conditions. As you could see on the figures, the model, the trained neural network was able to estimate with the good accuracy the 3 parameters between beginning of stem extension and grand maturity. And the green area index during stem elongation and flag leaf ligulation was estimated with a relative error of about 20%, which was lower than the error from measurements from destructive sampling. And under most conditions, the irritabilities of the retrieved traits was higher than 0.7. From the fraction of intercepted light and biomass estimation from destructive sampling, we can then calculate the radiation use efficiency of the canopy for different cultivars under different irrigation treatments. So one difficulty now is to relate variations of simple morphophysiological traits describing the structure and functioning of canopies to complex traits such as yield or protein content. And this is because of large genotype by environment, by management interactions. And this interaction can be deconvolved using process-based simulation models informed with parameter value estimated from phenomics and that are used to simulate grain yield or protein concentration. A key element here is to use models with algorithms that are close to the actual plant mechanisms. I'm here illustrating this using the classification of model for water stress response proposed by Parent and Tardieu, who identify models, classify model according to the way they respond to water stress, either in parallel where water stress has an effect on leaf expansion and radiation use efficiency, or in series where water stress has an effect on radiation use efficiency or photosynthesis, which then affect the biomass production and in turn will reduce the leaf area index calculated using a fixed specific leaf mass. These 2 types of model can provide similar results if carried out over several days. However, This choice has large implications in terms of candidate mechanisms and genes. And in relation with phenomics, this is well illustrated by model intercomparisons of these two types of models. You could see here on the left a model that considers the effect of water stress on leaf expansion and radiation efficiency in parallel. And in such a model, the leaf expansion started to decrease much earlier under drought than the photosynthesis will for a model that considers the effect of water stress on radiation use efficiency and leaf area index in series. The photosynthesis is much more sensitive and decreases much earlier under drought than shoot elongation. So if such a model are parameterized with sensitivities estimated from high-throughput phenotyping, they will give very different results. So to conclude, detailed canopy structure information can be obtained from high-throughput field phenotyping by coupling 3D architectural plants model with deep learning methods and radiative transfer models. Combined with short-term responses to abiotic stress obtained in semi-field or control condition platform, this information can be used to parameterize crop model and predict the performance of thousands of genotypes in target environmental scenarios. So I like to finish by acknowledging the contribution of several colleagues from INRA and CIRAD and the support of the French Phenomics project, Phenom Emphasis, and the Digital Agriculture project and the Solace European project. Thank you very much for your time. We'll be glad to answer your questions during the conference, on the day of the conference. And thank you very much for listening. Goodbye.